Okay, so I just wanted to come back and revisit an idea that I think I didn't explain too well in the first take of this video. Okay, so we're discussing proper time, and we've said that in your own frame, proper time is just the coordinate time that you measure. So we can call time coordinate tau, and then in your own frame, let's just say we're stationary in this frame A. We're just going to simply follow a world line that just traces out the time axis. So we could look at defining distances in our own frame, and we concluded that the line element has this fairly simple form minus c squared d tau squared, and that line element is essentially just measuring the length of this world line, and it's just going to correspond to effectively the amount of time which has elapsed in that particle's stationary frame. And then this time interval, because the line element is invariant, all other observers can agree on this time interval, and it's this proper time parameter now that we use to parameterize all of our world lines. So this is the stationary frame. Then we could say consider some other frame, B, in which this A particle is seen to be moving. So this yellow line is the world line of the particle A. And now the key point is that this proper time length is essentially fixed. It's invariant. So any length of proper time that elapses in your own frame is going to have to correspond to the same length of proper time as measured by this B frame. And now this is useful because essentially this ds squared, it always represents the length of a world line. So now the arc length of this world line of A as it appears in the B frame is going to have to be equal to the amount of proper time that elapsed in the A frame. And now just roughly and intuitively you can imagine taking this fixed length of delta tau. It lies completely straight along a tau axis or a time axis. But now if we look at how that length is going to appear in this other frame, well, this world line is no longer straight. If you like, it has some small components that point along delta x and delta tau. If we were to consider a small little portion of the world line, delta s squared, and we were to measure a small portion of that world line, I'll just draw it bigger here. If that white arrow which I've drawn, so if I just maybe draw it a little bit bigger here, this yellow arrow is representing the world line, and we know it's going to have a fixed length, delta tau squared. So this delta tau squared, which was fixed by the stationary frame, we're now looking at how that delta tau squared, the same length, is going to appear on the B frame. I've drawn it at a slight angle here, kind of to emphasize the fact that it's no longer going to be a purely temporal interval. It's going to have some space and some time interval components. But now we need to remember and realize that these are now the coordinate intervals that this B frame is measuring. So I think it would actually be better to call the coordinates of the stationary frame y, and the coordinates of the moving observer is going to be y, and the coordinates of the stationary observer are going to be x and ct. So now we're looking at how this world line length, this interval of proper time, is going to appear in this other frame, B. And now as we see, because this world line kind of traverses both the space and time directions, it doesn't just flow completely along the increasing time direction, this length is effectively going to have to be distributed across some combination of space and time intervals. And now this is where I kind of got myself a bit caught into one of my own traps in a previous take of this video, and I got really confused about this picture, and rightly so, because this picture is completely false or very, very misleading for the Minkowski geometry. We have to realise that this kind of right triangle picture is essentially the way that we visualise and think about distances in the Euclidean geometry. We're just essentially using Pythagoras' theorem here to express this length, delta tau squared, as delta x squared plus delta tau t squared. And so, using Euclidean reasoning now, we would conclude, okay, well this fixed length, delta tau proper time squared, is going to be greater than both of these coordinate lengths. But that's completely not true, and we always need to now remember that we're not in Euclidean geometry, so we can't draw a right triangle picture like this, because that of course relies on the Euclidean metric to define distances. But we now instead need to draw a Minkowski picture for the lengths in our geometry. Now I just want to point out that this intuition for this world line being straight along the tau axis in one frame and then having components along the x and t axes in the other frame, that's an okay intuition to have, but the intuition should be that this purely temporal interval, i.e. an interval that points straight up along a time axis, this temporal interval is now going to have to be, in some sense, distributed over space and time intervals to produce a world line that travels in not just a time or space direction. So how do we go about now visualising our Minkowski distance in a kind of similar, nice way to how we visualise these Euclidean or Pythagorean distances? So just to remind you, we had our metric, I'll just put it up here. This was the form of our metric, or our line element, and so this minus sign is what we see is causing all of these departures from the Euclidean behaviour. If that had been a plus, then we simply would have dx squared, dt squared, and then ds squared, forming a kind of Euclidean right triangle picture like this. But the minus sign there messes all of this up, and we can't use this Euclidean reasoning. So instead, and now this isn't too standard, it's just something I kind of came up with playing around with these formulae, essentially a way to sort of visually represent this line element in a similar way to how we represent the Euclidean right triangle picture. So now what I'm going to do is essentially just define a single line or axis that's just going to start at some 0 point, and then what I'm going to do is I'm going to say, okay, a vector pointing in this direction represents a positive addition to the value of ds squared, and a vector in this direction represents a negative addition, and then the overall kind of magnitude of the sum of all of these vectors is what's going to result in our value of ds squared. So let me just draw that now so you can see clearly what's happening. So we add on, in the positive direction, some amount dx squared, and then we subtract, i.e. by drawing a vector in the negative direction, some amount dt squared. And now for the purposes of this example, I'm just going to sort of forget about c, or rather just set it to 1. The value of c doesn't have any bearing on this picture, it's just effectively going to scale this arrow. So we can just ignore it and set c equal to 1 for now, which makes life a bit easier. But now these are our two vectors representing dx squared, and then the minus, you could, if you like, put a minus there, minus dt squared, and then these are added together, and now the overall result, which I'm going to kind of draw underneath this picture, well, we go a small amount that direction, but more this direction, is going to be some kind of vector like that, which is representing ds squared. Okay, so this picture might not make too much sense until I've drawn a few more of them, but I'll just explain again, just so you know exactly what I'm doing. So this kind of white vertical line is effectively representing 0, and then in that direction, this is a sort of just real number line, if you like. That way represents positive additions, so a plus dx squared, and then this way represents a negative addition, minus dt squared, and then the overall sum of these two vectors is the value of ds squared. And so I could have written the ds squared just on my number line just to keep consistent, but it's more useful to draw underneath so we can see how this interval is being distributed. And so now you can quite clearly see how all of our possible cases can emerge. We can simply achieve ds squared being negative, 0 or positive by just correctly scaling these two vectors. So if they're equal, then we get ds squared is equal to 0, and then if dx is greater than dt, we get positive ds squared, and likewise for negative. Okay, so this is just a kind of visual way to represent how these two intervals add up to make the whole line element, and it's just a way to visually represent distances in a way that our brains can kind of look and see, okay, well this ds squared, it's negative and it's going to be shorter than this dt squared and so on. So I'm just introducing you to this, and now I'm going to show you how it can be useful with this concept. So I'm going to draw a similar picture now, but kind of working the other way. We're going to start with effectively knowing the value of ds squared by looking at this d tau squared, and we're going to say, let's take a fixed interval of d tau squared and then see how it's going to translate into a dt and a dx. So let's start with our 0 of the picture, and now let's draw on our ds being equal to d tau squared. Remember I said we're going to set c equal to 1 briefly. So we're going to have some fixed length d tau, which we represent by a vector in this direction. So this is our d tau squared, and now this length of this vector is always fixed for all frames, and it's essentially fixed by the fact that it belongs to this observer who's stationary in their own frame. So this interval of proper time we can now translate into another reference frame, and we're going to see that it's going to have now not just a time component, but it's going to get some non-zero dx component. And so what we're going to have to do, well, we'll just first of all say there's going to be some now non-zero dx component. So this is going to be dx squared not equal to 0. And now in order to keep this dt squared the same length, we're adding on some amount dx squared. So what we're going to need to do is actually subtract now a larger amount of dt in order to keep the overall length the same. So this is now dt squared and minus dt squared. And so now very clearly from this picture, we can see that the coordinate time interval, as measured by the frame B, has to be longer than this proper time interval, which was measured by the particle A. So this is now a very important feature of relativity, that essentially proper time is the minimum possible time that is measured by any observer, and it's always the time that is measured by an observer who's stationary in their own frame. But now, as we've seen, allowing that observer to be viewed by some other stationary observer who sees this observer now moving in their frame, i.e. having some non-zero amount of dx, just from the fact that the line element, or just from the form of the line element, translating this d tau interval into some space and time interval, just because of the minus sign, if the x now increases away from 0, this dt is going to also have to increase to become more negative in order to compensate. Or rather, not necessarily just become more negative, just the value of dt is going to increase in order to keep the value of d tau the same. And so this, already now we're starting to see some relativistic physical effects without really doing too much work, by essentially just realizing that d tau has to be the same for all frames. We've now seen how this d tau is effectively going to be, well, it's going to be distributed across some coordinate time and coordinate space intervals, and these intervals are going to be different than the intervals that are measured in the stationary frame. And clearly now we can see adding any amount of dx is always going to have to make this dt larger than d tau, so that overall when we subtract this dt off, we're just always left with this constant fixed length. So now, to state the physical effect, we need to realise that this dt is the time that this b particle is measuring. So this b particle is essentially saying, okay, I see you moving through my frame, you must have elapsed this much time, or that's how much time I elapsed you to be measuring, but they're then going to realise, well, that time is a longer time than the frame or the particle itself measured. And so you'll usually hear this stated as moving clocks run slow, and we can clearly see from this picture that the stationary particle A is always going to measure the shortest possible time, and any other person that sees this A particle moving is going to think that their clock has elapsed more time than it actually has. So we're going to see a lot more of this, and we're going to be able to draw some really nice pictures on our space-time diagram to really clearly see this difference in time intervals. But now we're already getting used to this idea just by simply looking at this line element, and we're realizing that in your own stationary frame you can create these effectively fixed intervals of time that can then be translated into other frames, and because in your own frame a purely temporal or space-like interval is then going to achieve both time and space components in some other frame, the way that they add up is going to have to be different to the way that you measured them in your frame. And so you're always going to measure time distances as being the minimum possible distance in your frame, and then the other observer is going to associate a longer time interval to that same proper time interval. And now likewise, I could have just done a very similar argument by defining a purely space-like interval in the stationary frame, say some delta L, which we sometimes call the proper length, and then in any other moving frame, just using a very, very similar argument to here, we're going to have the delta L is always fixed, but then in some other moving frame there's going to be a non-zero delta T part, and so the coordinate system is going to assign now a longer length to that proper length, effectively. So another way of stating, well, the physical effect is that moving rods are shortened, and we're going to see all of these two physical effects in much more detail once we discuss Lorentz transformations. But I just want to now point out the fact that we've managed to see these physical effects coming into play without considering anything to do with coordinate transformations or moving to moving observers, we're simply just looking at these purely geometric objects, these intervals or the line element, and already just from the form of the line element we can see these physical effects emerging. And I just want to really point out that all of this is happening purely because we have this minus sign here, and so that we're not essentially using our Euclidean geometry anymore. We're using this kind of Minkowski, or sometimes referred to as hyperbolic geometry. So I kind of just invented this picture. I haven't really seen any other better way to represent it, but I think hopefully it's fairly clear. Positive additions to the line element can just be represented by a short vector or just a length going that way, and then we subtract a vector going this way, and how they overall sum up has to always correspond to some fixed interval, which is fixed by the stationary frame. And so this is just a nice way to kind of visualize how that fixed interval can become distributed over a coordinate space and time interval. So just to summarize then, I introduced this notion of proper time, which is the coordinate time, or just the time that you measure in a frame where you're not moving at all. And we saw that because of the invariance of the line element, this then effectively fixes for all observers the amount of time which has elapsed. And we refer to this as the proper time. And now when this stationary observer is viewed by another reference frame, their world line is no longer just going to be purely along the time axis, and so any ds is going to effectively have some contribution from both a dx and a dt component. Now we should be really careful in not using our Euclidean reasoning to visualize these components, because our Euclidean brain wants to view the components in this way. But now we need to remember that we're actually subtracting this dt component, and so this picture is not correct. We need to use a picture like this, and when we start using this picture we realize, well, having this fixed purely temporal interval, having this fixed, we have to then distribute our space and time coordinate intervals, and this is going to mean that one of them is going to effectively have to become larger than is measured by the stationary observer in order to keep the value as measured by the stationary observer constant. And so we're going to see this is essentially now going to produce the relativistic physical effects that we might be expecting, like time dilation and length contraction.